Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. My guest today is Ronald Mallett, Ph.D. He's an Emeritus Professor of Physics at the University of Connecticut. He's done some extra work on Einstein's general theory of relativity. He's published numerous papers on black holes and relativistic cosmology. So we're going to talk about the possibility of time travel based on, special and general relativity and some of the other implications of what Einstein had come up with. So welcome, Ron. Thanks for coming.
Well, thank you very much. Pleasure to be here.
If you don't mind, I'm sure that, the concepts are difficult for most people that don't think about them actively. What's the difference between special and general relativity that Einstein came up with?
Okay. I can tell you in a nutshell, the special theory of relativity essentially says that time is affected by motion. That by what Einstein meant by that was the fact that the faster a clock moves, the more time slows down. So time for a moving clock slows down. And when talking about a clock doesn't simply mean a mechanical clock. Your heart is a clock, for example, and the faster you move, the more your heart rate would slow down. Now, I should mention that you would not notice it. It's people who are watching you move fast. It's like when you're moving down the highway at 65 miles per hour, you don't feel that, but people see you zooming by. If they were seeing you go by quickly enough, they would actually see your heart rate, your metabolism slow down. So,
well, actually, if I was standing on the side of the road and I watched a car approaching and I was able to see someone's heart, wouldn't I experience like the Doppler effect as it approached me? And it would be faster, and then as it goes, here a woman passes by, and now it's receding into the distance, would then it be slower?
No, actually, as a matter of fact, what you're talking about is the frequency. Okay, that is to say that, and as a matter of fact, that's used in cosmology. As you're coming close, as the speed of light isn't changing, but what's happening is the frequency is changing and the wavelength is changing. So as the car is approaching you, if they had a flashlight turned on or their headlight turned on, it would actually appear as though the frequency is going up. In other words, the color would actually appear to get bluer. As the car is going away from you, would appear as though their tail lights, which usually are red anyway, but the tail lights would become redder. So when the light is approaching you, the light becomes bluer. As the light is receding away from you, the frequency drops and the light actually becomes redder. And that's in fact what happens when we look at stars. Generally speaking, we notice that the galaxies and stars, generally speaking, the light from them becomes redder because they are receding away from us. But
what happens with time, though?
The time is changing, but it's not changing in the sense you're talking about a different time that we're talking about here. What we're talking about is the clock that's at rest on board the vehicle itself. Okay, that is the time that we're talking about. So if you were looking at someone's clock, you would actually see the clock slow down as it's passing you.
Now we're getting to the speed of information. So like if there was a radio in the car, again, they're on their cell phone and they're talking to me, as they're approaching, the clock of their heartbeat wouldn't appear to change at all to us. And as they're receding away into the distance again, the speed of the clock of their heartbeat wouldn't be any different either.
Well, no, that's different. As I said, said, we're talking about two different effects here, okay? You're talking about the signal that's reaching you and the signal that's moving away from you. What I'm talking about is the time that's on board the clock itself, okay? That is actually slowing down, okay? It's slowing down. The faster the clock moves, the more the time is slowing down, okay? And that's independent of whether it's approaching you or receding from you. So that's you're talking about a different effect.
Oh, yeah, I apologize for my confusion and stuff, but can you just, break apart the two effects again and say why there would be a variance in both or not?
Yeah, the speed of light, okay, you should say the speed of light isn't changing, but what happens is that the faster an object moves, the more time slows down, okay?
Is there a reason why?
Oh, yeah, the reason is because time does not change. In other words, the light, the speed of light, you have to remember when you're talking about speed, okay? But if you're talking about speed is made up of the distance something moves and over the time that it moves over that distance, okay? So there's two factors in there, distance and there's time. And the thing is that normally when we're talking about the speed of an object, the speed depends on motion. I'll give you an example. Suppose that I'm throwing a baseball at you, okay? It's coming at you at a certain speed. Now, suppose that I run towards you and throw the ball towards you, okay? The speed that I'm moving will add to the speed of the ball. And so the ball will appear to become faster to you. In fact, that's what a pitcher does on the baseball mound. They use their motion of their body to add to the speed of the ball that they're pitching, and it's coming at you faster, okay? Now, the thing is that that's common sense. The thing is that we know that light itself, even though it appears to be continuous, light is actually made up of particles of light called photons. You could think of them as balls of light that are traveling at 186,000 miles per second, okay? Now, that's the speed so if I'm shining a flashlight at you, okay, then normally if I'm standing at rest and showing having the light towards you, the light's coming at you at the speed of light. Now, you would expect that just like with the baseball, for example, if I'm running towards you, these balls of light, these particles of light should be coming at you faster, right? Now, what happens is that it was a real experiment that was done at the end of the 19th century by two physicists, Michelson and Morley. What they did was they used the Earth as the vehicle, so to speak, and they shined light on the Earth. Now, if the Earth is moving, okay, which it is, then that motion of the Earth should add to the speed of light. But what they found is that the speed of light didn't change. That would be as though if I were running towards you with the flashlight, you would find that the speed of light is not coming at you faster, which you would think it would because of the baseball example I gave. That doesn't make sense. That would be as though I was telling you that if I'm throwing a baseball at you, okay, that no matter how fast I'm moving towards you, the baseball is going to be moving at exactly the same speed. And you know that isn't what happens. In other words, what happens in nature is that the speed of light isn't affected by the speed of the source of light. That was a major question. How come the speed of light isn't being affected by the motion of the object, okay? That was the puzzle. The thing is that what Einstein said is that remember what speed is. It's distance over time. And what Einstein said is the only way the speed of light could not change is that something else has to change to keep the speed of light from changing. And he said that something is time. Time has to change in order for the speed of light not to change. And that is reason why, and what he found out, he worked out mathematically, is that time actually slows down in order for speed not to change. Now, but it turns out that distance actually changes as well, okay? Distance has become shorter for a moving object. So time actually slows down the faster an object moves. Now, we know this really is what happens. Experiments have been done which show that the speed slows down. Two major ones on the microscopic level. We've seen that there's a device that's called the Large Hadron Collider in CERN, Switzerland. This device accelerates particles, elementary particles. All of these particles have different lifetime, okay? Now, the thing is that this lifetime, normally one would think is fixed, but what they do is they find out that when they speed up these particles close to the speed of light, they find that the lifetime, the internal lifetime of these clocks, of these particles, is like their clock slows down, so that when they accelerate these particles, they can get these particles to live 10, 20, 30 times longer than they normally would. So we know that time actually slows down. We've seen it not only on a microscopic level, but on a macroscopic level. Most people don't realize that in the 1970s, there was an experiment that was done at the Naval Observatory. What they did was they took an atomic clock that they kept at rest at the Naval Observatory, and they put another atomic clock on an ordinary passenger jet. When they flew the plane around the world, what they found was that the clock, when they brought the passenger jet back, they found that the clock that had been on the passenger jet had actually slowed down compared to the clock at rest at the Naval Observatory. So we know that speed affects time. The faster a clock moves, the more time slows down.
Wait, that's crazy.
Yeah. And as I said, the reason for that happening is the fact that the speed of light isn't affected by motion at all. And that's just built in.
If you had like a kind of like a chemical synthesis, something happening in chemistry that normally occur in the order of, let's say, a femtosecond, and you put it on if you made it travel at like 0.9 C, what would happen to the experimental byproducts? Would there be different, we have a big yield because it's happening in a different time frame now, it's happening in a slower time frame, or because of the frame of the stuff on board at which
it would actually happen at a different rate from the standpoint of us watching it. It would be happening at a different rate. Now, when we come back, we'd actually find that this is a permanent effect. To give you an example of that, once again, on a human scale, this is an example that Einstein uses called the twin effect. Suppose that you had a twin brother and that they were planning on let's say going to a star that was, 25 light years away from us. Okay. Now, the thing is that suppose that they make that trip and they're traveling close to the speed of light. In other words, that you put it out, let's say it's 0.9 the speed of light, percent. So the thing is that when they come back, depending on how fast they were going, their clock is slowing down. Yours on the Earth is staying at its normal rate. When they come back, since let's say the star was 25 light years away, if they're traveling close to the speed of light, it's going to take them about 25 years to go out and 25 years to come back. So from your standpoint, it would appear as though your twin took 50 years for them to come back. Now, you'll be 50 years older. However, their clock is slowed down. When they come back, depending on just how fast they were going, they may only have aged 10 years. That is really only 10 years. So even though you're 50 years older, they will only be 10 years old. That's a real effect. If we had rockets that could go close to the speed of light, we would actually see that as a real effect. So when they come back, yes, the processes that were going on would have happened at a different rate than what they would have here on the Earth. Okay. So in fact, that's what we mean by time travel. In other words, when we talk about time travel into the future, that's the effect that we're talking about. And in fact, they got that right in one of the famous science fiction movies, Planet of the Apes. The astronauts went out and came back and they thought they had landed on another planet. It turns out that their rocket had been traveling close to the speed of light and they had come back in the Earth's distant future. And this is a real effect that's based on this. And as I said, we've actually seen the baby steps of that in the experiments that I told you at the Naval Observatory and also at the Large Hadron Collider. So this is a real effect. Time travel to the future not only is possible, it has been done, and it's based on Einstein's special theory of relativity. Not by that. By the way, that theory was developed in 1905. Now, it turns out that Einstein developed a second theory, and the reason why he developed the second theory was that everything that he looked at, he made sure that the equations had been modified to take into account the fact that time slows down for speed. But it turns out that the only thing that didn't seem to be affected by that was gravity. It turns out that according to Newton, gravity it travels instantaneous, it travels faster than the speed of light. Now, why would that lead to a paradox? Suppose that we were, let's say, considering a cosmic catastrophe. That the Earth is 93 million miles away from the sun, and that it takes light about 8 minutes to get from the sun to the Earth. Now, what would this mean if, let's suppose there was a cosmic catastrophe that would destroy the sun? From our standpoint, it would take 8 minutes for us to actually see the sun destruction, because it would take 8 minutes for that light to get from the sun to the earth. Okay. Now, the thing is that according to Newton, however, gravity shuts down instantly. So you would have the following weird effect. We would still see the sun in the sky for a full 8 minutes, but since gravity travels instantly, as soon as the sun was destroyed, the earth would have nothing to keep it in orbit around the sun. So the earth would be going off. We would find ourselves going off into space, and we would still see the sun sitting out in the sky. So Einstein said that implies that gravity is traveling faster than the speed of light. And so he developed a whole new theory of gravity in order to change that. And his whole new theory of gravity is what we call the general theory of relativity. Now, you might say, what is this whole new theory of gravity? What he said is that what we call the gravitational force is not a force at all. It's a property of space itself. I'll give you a simple example. Suppose you had in front of you a small trampoline, let's say a rubber sheet, just a small, tight rubber sheet. And suppose you put a bowling ball on that rubber sheet. It bends the rubber sheet. Now, suppose you put a marble on that rubber sheet. The marble will, of course, roll down towards the bowling ball. Now, suppose that I still have that rubber sheet, the bowling ball, and the marble. But let's suppose that the rubber sheet is transparent. It's there, but it's transparent. So the only thing you can see is the bowling ball and the marble. So I release the marble, and the marble moves towards the bowling ball. Now, since you can't see the rubber sheet, you would say, aha, what's happening is the bowling ball is somehow pulling on the marble. Well, we know that isn't what's happening, okay? Einstein said that's in fact what's happening in empty space. The sun is actually curving the empty space around it. We can't see the empty space being curved, but that's what's happening. And that it turns out that the Earth is actually moving along that curved space. In fact, you could do the same thing with the marble. If you have the bowling ball and the rubber sheet and you give the marble a little bit of a sideways motion, you could get the marble to sort of orbit the bowling ball.
Well, what are you curving if it's vacuum out in space?
Vacuum
is some phone?
The thing is that space is a vacuum, but it actually has a structure to it. We just aren't aware that it has structure to it, okay? It's a vacuum, but it actually has a structure. That's the strange thing. We think of the fact that a vacuum means there's nothing there. Space is there, and that empty space actually can be deformed, according to Einstein's theory. Prior to that, we didn't know that could happen, but Einstein said that that's actually what's happening, that empty space actually gets curved. That's this analogy that I'm using with the bowling ball and the rubber sheet. It's just that, an analogy. But what the sun is actually doing is curving the empty space around us. And even though we can't see it, we can see the effect of that. And that's what gravity is, okay? So the Earth is actually moving along this curved space, something like a skater on a roller derby ring, okay? And that is, in fact, what we call gravity, okay? Gravity is not a force. It's actually a bending of empty space. Now, this actually has a direct consequence, one that we verified very recently, okay? Suppose that the sun is destroyed. What it would do, now let's go back to the rubber sheet and the bowling ball. Suppose I take the bowling ball suddenly off the rubber sheet. What happens? The rubber sheet starts vibrating a little bit, okay? That's what happens to empty space. What Einstein has said is that the Earth was destroyed, the empty space itself would vibrate. We can't see that, but it would be vibrating. Those are what are called gravity waves. And those gravity waves are something that have been directly detected, okay? In fact, just a few years ago, and in fact, the Nobel Prize was won for the detection of these gravity waves that show that, for example, when two black holes collide, they actually cause a vibration of empty space. Now, what's important with Einstein theory is the fact that if you calculate how fast those vibrations go, in other words, if the sun was destroyed, the vibrations of space itself, the calculation showed that it would take the speed of light for that to happen, okay? In other words, the vibrations don't travel instantly. The vibrations travel at the speed of light. So I don't know if you would think of it as a consolation, but what this implies is that if the sun were destroyed, the vibrations of empty space that would reach us would take 8 minutes. So that if the sun were destroyed, not only would we still see the sun in the sky for 8 minutes, but it would take 8 minutes for the effect of gravity gravity to shut down. So that brings gravity back into relativity. So now that's what we mean when we talk about a relativistic theory of gravity. So the general theory of relativity implies that gravity is the bending of empty space. Now this means that what this Earth is doing is that even though you don't see it, when you jump up, what's happening is that the Earth actually has curved space around you. And so it's actually, you're moving along the curved space that the Earth has created, and that's what's pulling you down. As weird as it sounds, that's it. So the difference between the special theory and the general theory of relativity is the following. It turns out that, remember I said that space now is curved by matter. In Einstein's theory, space and time are linked to each other. And in fact, that's why we call it space-time, okay? So the more an object curves space, the more an object actually is bending time. And what do we mean when we talk about the bending of time? The bending of time shows up to us as clocks slowing down in a gravitational field. What I mean by that is clocks here at the surface of the Earth are actually going a little slower than clocks at a high altitude, okay? So the stronger gravity is, the more time slows down. Now you might say, whoa, wait a minute, has this been shown? Not only has this been shown, it's part of our everyday life. The GPS system works because of Einstein's theory. Let me tell you exactly how that works. The way your GPS system works is the fact that your unit in your car has a little clock in it, okay? The satellites have clocks in them, okay? The satellites send a signal that's at a certain time that reaches your unit in your car at a certain time, okay? Now, it turns out that in physics, there's a very simple relationship between time, speed, and distance. If you know any two of those, you can calculate the other. In other words, if I know time and I know speed, I can compute distance. It's a very simple relationship. So that means if I know the signal, the time the signal was sent by the satellite, and I know the time that it was received by the unit in your car, and I know the speed of the signal, which is the speed of light, then I can compute distance. That's how the GPS system works. But when they were setting it up, they were assuming Newton's theory of gravity. Why is that? Because Newton assumed that nothing, not speed, not gravity, nothing can affect time, according to Newton's theory. That's important. So when they were setting up the system, they were assuming that the clocks on board the satellite were actually ticking at exactly the same rate as the clock in your car, according to...
Oh, so how much of an error would that lead to in early GPS?
It turns out that it's a significant error. When they were setting up the system, because they assumed that the clocks in your car were actually ticking at exactly the same as the rate of the clocks in the satellite, it was giving wrong location. That was a significant effect. So they had to consult with physicists to find out what was going wrong. And they said that what you have to do is you have to take into account Einstein's theory of gravity, because the clock in your unit in your car, according to Einstein, because it's closer to the surface of the Earth, it's actually ticking a little slower than the clocks on board the satellite. Computers have to be used to take that difference into account. And when they took that difference into account, the system was working perfectly. So this effect of Einstein, it shows that this is not just simply a theoretical effect. This effect of gravity on time is real and practical. And I think of us, I tell people that they should give a slight mental nod to Einstein every time they use their GPS system, because without his theory of gravity, we would not have a working GPS system. So we do know that gravity affects time. And that's important, because the thing is that it turns out that this allows for, now when we were talking about, let's go back to the special theory of relativity with speed. Remember I said that because of the fact that clocks slow down the faster you move, it leads to the possibility of time travel to the future. But no matter how fast you move, you can't go back to the past. It turns out that Einstein's general theory of relativity allows for the possibility of time travel to the past. Now, how is that possible? Well, it turns out that there's objects that people have heard about. There's collapsed stars. When a star collapses to a certain point, it can pull all the light that tries to come away from the star back to it. In fact, that's what we call a black hole. A black hole is nothing more than a star that has started its life, its energy has given up, and the star starts to collapse. As the star starts to collapse, the gravity around the star becomes so great that it pulls all the light to it. So if you're standing outside the star and all of the light is being pulled back to the star, what do you see? You see nothing. And that's what we mean by a black hole. Black hole is just simply a star that has collapsed to a point that all the light that tries to get away from it gets pulled back to it. Now, it turns out that black holes can also affect time. Two effects can occur. The stronger a black hole is, or the more massive a black hole is, the more time will slow down. If you get close to a black hole, time will start going slower and slower and slower. As you're watching someone who's going towards a black hole, their clock will actually slow down. Time for them will go slower. As you get there, they will age less. And in fact, there was another movie that got that particular effect right. Sometimes the science fiction movies do it. This one was a really great movie called Interstellar.
Yeah, I remember that movie. It's freaky.
Yes, it's a fantastic movie. In that movie, I remember there was a sequence in which the astronauts landed on a planet that was close to a black hole, and they had their fellow astronaut stay on board the rocket that was far away from the black hole. And the astronauts who were on the planet, their clocks were running slower than their companion's clock on board the sat of the rocket. And when they came back, in fact, they found that he was older than they were because they had been on board the planet. That would be a real effect that if someone was near a black hole, by the way. So that part of Interstellar got it right. But in any case, it turns out that if you're getting close to a black hole, time slows down. But now suppose that not only that could happen, but suppose that the black hole was rotating. A rotating black hole can do more than just simply, there'll still be the slowing down effect, but a rotating black hole will affect time in a whole different way. Here's a way to think about that. A rotating black hole will actually cause a twisting of space itself. Remember, space is acting like a medium. It acts like a medium. So if I rotate a black hole, I can actually cause a twisting of space. You could think of this as being like,
but if there was no ether, there's true vacuum.
So it's this vacuum. Well, it's not you keep using the word vacuum as though vacuum is that it's absolutely true that it's empty space, but the empty space itself has structure. You have to, and it's hard for us to conceive of that, but the empty straight space, even though it's empty, it does have a structure associated with it. And it's not an ether, and it is a vacuum, but it actually behaves as though it was something that could be deformed. So it's literally deforming of empty space.
What has experimentation shown about the nature of fabric of space? What is it? That's what it looks like. Has anyone modeled it?
The way in which you might say the way it shows up to us is what we call gravity. In other words, if you don't have any objects there, then it just has no effect whatsoever. But as soon as you put a massive object there, that's when the empty space becomes deformed, even though it's a vacuum, and it shows up to us as gravity. So you might say the experimental effect of the empty space being bent is what you call gravity. That's why I was using that analogy of the bending of the rubber sheet. But the point is that this empty space itself only appears to us as having structure when we have a massive object in it. For example, the sun or the earth or any massive object. You are actually bending the empty space around, but it's so minuscule that you don't notice any effect of it. But the more massive an object is, the more this empty space is actually being bent. So the way it shows up experimentally is what we call gravity. And in fact, it bothers me sometimes popularizers don't get it right, because sometimes what they say is that gravity causes the bending of empty space. No, gravity doesn't cause the bending of empty space. Gravity is the bending of empty space. It's a slight difference in language, but that's key. Gravity does not cause the bending of empty space. Gravity is the bending of empty space. Okay.
So what can be intuited about the structure of a vacuum?
The intuitive thing is that, as I said, it's not intuitive.
No, but what can be understood about the structure of empty space? It's got to have...
That's it. The structure of empty space, as I said, does not show up until you put something in it.
Oh, I know, but once you do, can you experimentally...
Oh, yeah.
What has been determined experimentally that the structure...
Well, that's it. As soon as you put something in there, the structure shows up as gravity.
I know, but beyond gravity, if you have like a high vacuum...
No.
Well, if you have a constant high vacuum and you put like a metal ball in there, what would that do to...
Remember what you just simply said? Remember what I just simply said? No. Before you put the metal ball in there is nothing. There is no structure that you would know. It's when you put the metal ball in there, the structure appears. And the appearance of the structure is what we call gravity. That's very.
Let's find the structure appears, and now there's gravity. But what else, in a dimensional sense? Length, width, height, depth. What does the structure of the vacuum look like now?
Well, that's it. It looks like, in fact, the example that I gave you, literally, if you could see it, you would actually see. That's why I use that analogy of the bowling ball with the rubber sheet. Remember how a rubber sheet would look if you put the bowling ball in it? It would be a dimple. That's exactly how the vacuum would look if you could see it. It would look like that structure that is a curve of the space.
Well, I don't know if would it? How do we know? Maybe it's just, that's a proxy for something that we can, say, okay, that makes sense. But there's got to be some actual change. Again, the structure of that, the actual, like the quantum foam, I guess appears and disappears in the vacuum. But
foam, once again, it's due to the process of matter. Matter, in other words, in the special theory of relativity, for example, there is no structure to space, that it's just flat space, period. It's when you put matter into the structure that the structure appears. Prior to that, you would not see any structure. Okay. So the effect of what we call gravity is what tells you what the structure looks like. So if you want to know what the structure looks like, once you put an object in there, you could map out what it looks like by mapping out how gravity changes as you move away from the source of the gravity. Okay. So it's the object that is, in a sense, giving structure to the space. That's it.
I don't know. It's been over 100 years that there's been experimentation happening and everything. There's got to be some discernment of what's there, or is it total consideration?
Discernment. The discernment is gravity. You're asking what is the effect, and the effect is what we call gravity. There is no gravity without the object being there. In other words, there is no structure there without the object.
So I guess black holes are very useful because the gravity is so intense, the warping is so intense that you're more likely to discern something rather than nothing, I guess, in those situations.
Yeah, but you discern it already. Remember I talked about your GPS. Your GPS is actually discerning the structure. Without that, in other words, according to Newton, there is no structure out there. So if literally, according to Newton, your GPS system shouldn't be working, okay, because there is no structure. It's literally because of the fact that what you have is the Earth. The Earth is actually causing a bending of space, and that bending of space is occurring in the satellite. There is no bending of space. And so
what is light, as light or electromagnetic radiation goes through, intergalactic space, what is it going through? What is it passing
through? Empty space. But that electromagnetic radiation has energy to it. So that
as a paradox, though, it must be affecting the structure of empty space somehow as it goes through it.
Oh, it definitely is. Light itself. In fact, that is part of what my work involved. In other words, in Newton's theory, okay, light does not create gravity. That's important. The only thing that can create gravity in Newton's theory is matter. It turns out that light, even though light doesn't have matter, light has energy, but that's important. Remember, there's another basic equation that comes from Einstein's theory. The questions you're asking, by the way, are great. Remember the very famous equation that now every school child knows, E = mc squared? That's important because that equation actually tells us that matter and energy are equivalent. When I say that equivalent, that does not mean that they're the same thing. Okay, people make that mistake, but it means that matter and energy are equivalent. Matter is something solid. Energy is not, but they are equivalent to each other. And that factor of equivalence is the speed of light. That's why it's E is equal to mc squared. So when I have a little bit of matter, that means that I have a lot of energy. Most people think of that equation in terms of the fact that if I have a little bit of matter, I have a huge amount of energy. That is what we talk about when we're talking about atomic energy, by the way. We convert a little bit of matter into an enormous amount of energy, and that gives us atomic energy and the atomic bomb. But the thing is that it works in the other way, both directions. Now, what that means is that if I have pure energy, which light is, electromagnetic light is made up of electromagnetic waves, and those electromagnetic waves have energy. They don't have mass, but they have energy. But that means I can read the equation in the other direction. If I have a certain amount of energy, that means that's equivalent to a certain amount of matter. And so since matter is what is causing the bending of space, that means that the energy of light can also cause the bending of space. And it turns out that in fact, the breakthrough in my work was the fact that, remember I said that gravity can affect time. We know that, okay? And we have that demonstrated with the GPS system. But this means that if light can create energy, which light is energy, then, and that's equivalent to a certain amount of matter. That means that if light can create gravity and gravity can affect time, then light can affect time. And that was part of the breakthrough of my work. Was that what I found was that if you have a circulating beam of laser light, a laser light is a fantastic source of light, a unique source of light. What I found is that a circulating beam of laser light will actually cause a twisting of empty space. And that twisting of empty space will show up by the fact that if I put a particle in the zone where the circulating laser light beam goes, it will actually get twisted. That spinning piece of matter will actually get twisted by the empty space inside the circulating beam of laser light. I did this mathematically, by the way. I should mention I'm a theoretical physicist. Einstein was a theoretical physicist.
What would you expect to see if the structure of the space was twisted?
That's exactly the point. Suppose that I have a spinning particle. A spinning particle would have an axis of spin, just like the Earth. You know, the Earth rotates and it has an axis of spin. Okay, a spinning particle, subatomic particle, all spinning subatomic particles have a little axis of spin. Okay, and suppose I take one of these subatomic particles and I throw them in that region where the circulating light beam. Now you wouldn't be able to see. You wouldn't see the empty space being twisted. But what would happen is that the empty space would twist that little spinning particle. It would twist its axis and spin. So you would be able to see the axis of spin getting twisted when you turn on the circulating beam of light. So that's how you would know that the empty space is actually being twisted. So when you turn off the circulating beam of light, the axis would no longer be twisted. But as soon as you turn it on, the axis would get twisted. So that's how it would show up experimentally. And in fact, that's the prediction that my equations show. Experimentally, it hasn't been done yet, but that's what it's based on. So my work is based essentially on Einstein's theory that matter and energy can cause structure of space and time to become bent and warped. And if you have a circulating beam of laser light, will cause a twisting of space. What I also found is that this twisting of empty space could lead to a twisting of time as well. And that twisting of time will show up in a very interesting way. I can give you an analogy. Suppose that right now in front of you have a piece of paper, an ordinary piece of paper. And let's suppose you draw a straight line on it that represents a timeline, okay? At the bottom of the line is the past. At the middle of that line is the present. And at the top of the line is the future. That is called a timeline. And that's the way in which it's represented in Einstein's theory of relativity. In other words, all of us throughout our life, we're moving along this timeline from the past to the present to the future. But suppose that I were able to twist space, empty space. Time and space are linked to each other. Whatever I do to space also happens to time. So if I'm twisting the empty space, imagine a straight line. Imagine that I take that straight line and I make it into a loop, okay? Then I could move from the past to the present to the future. But I'd made that timeline into a loop so I can go from the future back to the past. So
or if you could slow down, I mean, if you could essentially sleep in like hyperspace, let's say you'd have a book called like, cat naps in hyperspace. So therefore, at least when you're sleeping at night, you could somehow not age as fast as everyone else.
Well, you have to, there's two ways of doing it. One is the fact, as I said, you have to be moving fast enough for that to happen. But that could happen if you were moving fast enough. But the way in which you could get time to get bent is by having circulating, in other words, a rotating black hole will cause this twisting of space that I was telling you about. And it could cause the twisting of time. So if you go into a rotating black hole, you could actually go back into the past.
Yeah, so it caused like a layering of the past, like depending on the layer that you got entrained in that twisted space would to tell you, how slow you go according to our frame, according to an outside frame.
Well, when you're going towards it, time would slow down, but due to the rotation of the black hole, it would cause you not only time to slow down, but you could also cause time to become twisted, and they could allow you to go into the past. Okay, we know that this slowing down happens for time when you're gravity. We haven't seen the effect on time yet because that's a much more that it requires much more energy in order to cause this twisting of time that I'm talking about. But it could theoretically happen. And we know that the link is there. And as I said, we already know that. In fact, there's an experiment that is actually seeing the fact that the rotating Earth will cause this twisting of space. It's called Gravity Probe B, in which what they did was to put satellites in orbit around the Earth, and the direction of the satellites are actually twisted due to the rotation of the Earth. So we know that that effect occurs for rotating matter. We haven't been able to get the experimental effect for the twisting of time because that requires the twisting of space to become as great as what would happen for a rotating black hole. But also theoretically, once again, and Mike, when I say theoretically, I mean mathematics is what I use when I'm saying this word theoretically. We've been able to show that the twisting of time could occur too. And with my work, once again, which is anchored in Einstein's theory, I've been able to show mathematically that a circulating beam of laser light will cause a twisting of space. And if the energy was great enough, then that should actually allow for a possibility of a twisting of time as well.
Yeah, but if you went like locally backwards in time, and then you popped out of the twisted part of space into, regular time, how could you go backwards? You'd be popping into a time that would have passed, even if only a small amount of time at that.
No, well, see, that's what's important. You have to remember that. In fact, it answers a question that was posed by Stephen Hawking. In other words, suppose I tried to go back into the past. How come we're not seeing time tourists from the future? You can't go back into the past earlier than when the device is turned on. In other words, suppose that I was trying to go back into the past. If I turn the device on today, it's what's starting to cause the twisting of time into a loop. So suppose I turned it on today and I let it on for 10 years, then I could send information back, for example, 10 years, 7, 5, all the way back up to the time I turned the device on. I cannot go earlier.
Gotcha.
Okay. And that's important.
So could you structure time so that you would be in a loop where essentially no time passes to the outside world, even though it passes for you?
Only, when you got close enough to, at least from the standpoint,
like time stalling.
That's right. That would happen if you get close enough to a black hole, you could actually get time to go what appear to be zero. In other words, for someone standing outside, it would appear as though time has stopped for you. It would appear as though you're sort of frozen in time if you're close enough to a black hole. Yes. Yeah. But once
it's like they would say, get a law degree in your spare time. If you're able to do this, you could, time would pass for you, but at least you can get things done apparently instantaneously to the outside world.
Yeah, right. No, one way of doing it. But the thing is that once again, it's all of these things are anchored in Einstein's theory. And as I said, we have seen experimental evidence of this. So it's real. So
how much of Einstein's theories did he live to see the verification of, and what did he not see?
He was able to see the verification of almost all of it. The reason why he saw the verification of the special theory of relativity is the fact that he saw the effect of that as far as atomic energy is concerned. But as far as the effect on space, that was what led people to know that his general theory of relativity was correct to begin with, because what he predicted was that the light around the sun, normally if gravity, once again, it wasn't something that was predicted by Newton, but the sun, let's suppose that you have a star that's right behind the sun from the standpoint of what us here on Earth. You couldn't see it. It's like someone standing in front of you. You can't see that person, or you can't see. Okay. So if something is right in front of the object you're trying to see, you can't see it, right? So suppose there's a star out in the sky that's behind the sun. You would not be able to see that star normally. But what Einstein said is that the sun is bending the empty space around it. So the starlight that's coming from that star, as it gets near the sun, that light will get bent. So the light that's coming from that star will get bent and it would reach us. So even though it's behind the sun, the light from that star could still get to us. So we would be able to see a star that's behind the sun when we shouldn't be able to see it. That his prediction was.
So some of the light bends around it.
Right, exactly. And so that was his prediction. So he's predicted that if the sun actually was curving the empty space, then we should be able to see objects behind the sun that we should not be able to see. And an experiment experiment that was done, the way they did it was that they looked at a portion of the sky where stars were at. And then during a total eclipse, when the sun was in front of those stars, but the sun's light was blocked out, they looked and they were able to see stars that they shouldn't have been able to see normally. And so that was his prediction. And that's what led people to know experimentally that the general theory of relativity was correct. So he was able to see both the predictions from the special theory and the predictions from this general theory of relativity in his own lifetime. What he wasn't really cool, right, were things like black holes and things like that. That didn't happen until, much later. But he did make these predictions that were seen. And of course, that's just the tip of the iceberg of what Einstein did. His work led, in fact, to lasers. I mean, theoretically, he actually predicted what we call a laser way back, so there were many, many other things that Einstein predicted that is part of our life. All the things that I've been talking about, I've actually published the book, which is both a memoir and a basic science book that's called Time Traveler, a scientist's personal mission to make time travel a reality. It's so people might be interested in that. The book is available from Amazon. Also, a backstory that people would, to just mention, you might say, why is the scientist interested in time travel in the first place? It had to do with the death of my father. When I was 10 years old, my father died at 33, and I was devastated. It was when I read H.G. Wells's book, The Time Machine, that I became interested in the possibility of building a time machine to go back to see him. And I realized later that I was going to have to understand Einstein's work in order to see that possibility. And that is, in fact, what led me to become a theoretical physicist. And
that's really cool. Well, excellent, Ronald. So just restate the name of your book, and that would be a great entry point for people to go further with this. What is it again?
The name of it is Time Traveler, and the subtitle is A Scientist's Personal Mission to Make Time Travel a Reality. But the name of the book is Time Travel. Once again, incidentally, there has been some interest in Hollywood in making a feature film, and I'll keep you posted on how that comes out.
Okay. Oh, that's great. Well, very good. Well, thank you so much for coming.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.